Good afternoon. This is video number 296. How does change in units of measurement of dependent and independent variable affect the regression results? In today's video, I'll discuss to answer a number of questions regarding what happens if we change unit of measurement. Let us suppose we want to evaluate the results of regression of y on x, and there are two researchers. One researcher uses data in billions of euros for both y and x, but the other researcher expresses data in millions of euros. The question is, will the regression results be exactly the same in both cases, or they will be different? If not, which results should be used? In other words, the question is, do the units in which the dependent and explanatory variables are measured make any difference in the regression results? If so, what is the sensible course to follow in choosing units of measurement for regression analysis? My dear students, this is very simple. We will compare the results of various regression output in which y and x will either be measured in billions or in millions, or one is in billions and another one is in millions, and vice versa. So we will like to evaluate the effects of change in units of measurement on the regression output. To answer these questions, we will proceed with the help of a numerical but a hypothetical example, and we will use the following regression model, where y is a function of a hat plus b hat x plus e, where y defines sales revenues either in millions or in billions of euros, and x stands for advertising expenditures which are measured either in millions or in billions of euros. A hat and b hat are constant or intercept and regression coefficient respectively. So we will do that. So in order to show you the results, let me go to the stata and let me clear this old data. So let me open my file, and here is my file. Let me show you the data. There are four variables, y, and y means sales revenues, but here we have measured these values in billions, and this is advertising expenditure, and these values are also in billions. And then here y mil shows that these values are in billions. We have multiplied this column by 1000, so we get sales revenue in the millions. Similarly, we have multiplied this second column by 1000, and this gives us another column x mil, which means that x has been measured in millions. Now I will regress y on x, we will see the result. Then I will regress y mil on x mil, and we will see the result. Then we will try to regress y on x mil, and then we will try to regress y mil on x. So let me first test the first result, and the command is here regress y on x. So both the variables are measured in $billion. So here are the results. This is ANOVA, and here it shows model sum of square or regression sum of square. These are residual sum of square, these are total sum of squares, and these are number of observation, F statistic is 45.77, and this is probability value of F. The constant term is equal to 7.6, its standard error is 6.33, and its t value is 1.20, and the coefficient for x variable is 3.533, its standard error is 0.522, and its t value is 6.77. So it means if advertising expenditure increased by 1 billion, sales revenue on the average will increase by 3.533 billions. If advertising expenditure were 0, then on average total sales revenue will be equal to $7.6 billion. Now let me regress y in million and x in million. So the results are here. Now this time you see the standard error and its the coefficient and its standard error are now 1 times of the corresponding values in the previous regression. It was 7.6, now it is 7,600, and its standard error was previously 6.33, now it is 6,332.324. However, the t values in both the regressions are exactly the same. R square is the same here and here. Adjusted R square is the same. F statistic is the same, and p value of x is also the same. Now in the third regression, I will regress y, which is in billion, and x in million, and here is the result. Now this time the intercept term and its standard error remain the same, whereas the coefficient and its standard error are 1 divided by 1000 of its values in regression number 1. However, t values are still the same. F statistic, its p value, R squared, and adjusted R square are also the same. And now let me try the other regression in which I will regress y in million and advertised expenditure, which are expressed in $1 billion. Now F statistic is the same, its p value is the same, adjusted R square is the same, R square is the same, t values are the same, but now this time the slope and the intercept term as well as their standard errors are 1000 times of the values in regression number 1, in which both the variables were measured in billions. So we must note that in all the regressions, R square value remains the same, and this is not surprising because the R square value is invariant to change in the units of measurement, as it is a pure or a dimensionless number. Similarly, F state value remains the same, t values remain the same. So this is how interpretation of the results change if we change units of measurement either for both dependent and independent variables or for either of them. I hope you got a good idea regarding change in the units of measurement in regression results. If you have any question, you may ask your question in the below comments, and I will try my level best to come up with the answer. Thank you, and see you soon again. So here I have also combined all the results. This is for the regression of y and x, and both the variables are measured in billions. Here x and y are measured in millions, and you can compare the coefficient 3.53, 3.53. So in this case the slope coefficient remained the same, but the standard error, here it was 7.6, but in this case when both variables are measured in millions, it is 1000 times higher than this. And similarly, the standard error of the constant also is 1000 higher than this value. But the standard error of the coefficient, the regression coefficient, remains the same. Here, in this part, we have regressed y in $1 billion on x in $1 million, and in this case the constant and its standard errors remain as before, but the coefficient and its standard error are now 1 by 1000 of the coefficient and its standard error in the original regression. In the fourth regression, we have regressed y in millions on advertising expenditure which are measured in billions, and in this case both the constant and the coefficient, the slope coefficient, as well as their standard errors are 1000 times their corresponding values in the original regression. So you can compare these results in this one slide. So I hope this is quite interesting for you. If you haven't yet subscribed to this channel, kindly do subscribe, and do not forget to click on bell icon so that you can get notification about my other videos. Thanks for watching.